Okay, so we're going to go over function notation. First off, function notation is a little different from what we're used to seeing. This question, when you go to graph it, still pretty much means y equals 12x minus 2x squared. This would be a quadratic function because we have an x squared. What function notation does is it helps you in terms of when you're going to plug things in. And it's just something we go to refer to. That way we don't get too confused because y can also be used as another variable. We're talking specifically about an equation here. So we use this to represent that equation, the output, you would say. So the f at x, whatever f at x is equal to, will be the final output, and your x is the input into the equation, so what we put in for the variables. Now it sounds very confusing, but we'll go through a quick example here. Okay? The very first one they've given us is still ask us to find f at 5. Okay? Now, the function f, or f at x, this is that function. And what they're saying is, if your variable is the number 5, what will f at 5 be? Okay? So this function we're talking about right here, if the variable is 5, what is it going to equal? And that's what f at 5 represents. It's almost like saying y. So in other words, what I do is I take the equation, and I take 12 times, instead of x, we replace it with the number 5, minus 2, and instead of x again, we replace it with 5 squared. 12 times 5, do you know?
60.
Yep, that's right. Subtract 2 times 5 squared is
50.
not quite. 5 times 5. 25, yeah. And then 2 times 5, we get 50. Oh, maybe that's what you're going for.
That's what I said.
Okay, sorry. And then we get 10. So what this means is f at 5 is equal to 10. Okay. Now they can give you the same type of function and give you a different input. For instance, they've used negative 2 on the second one here. Okay. So you have 12 times negative 2 minus 2 squared. I'm going to zoom in a little. That's better. Okay. So it's the same idea. And we go about solving the exact same thing. The only difference is we're using the same function, like we said before. The only difference is the input is different. We've changed x to negative 2. So 12 times negative 2, 24. Negative 2 squared would give us 4. Okay, so we have negative 2 times 4. Negative 24. Negative 2 times 4 is negative 8. And in the end, we end up with negative 32. So a big difference in terms of what our input was, right? When f at 5 was equal to 10, f at negative 2 is equal to negative 32. We could use those as points too, this being our x value 5 and this being our y value when we go to graph it. So you could almost write it like, if you wanted to graph this point, you would say your x value is 5, your y value is 10. And same idea here, x value is negative 2, y value is 32 in terms of plotting and graphing. Okay, so our second example here, we have two equations. The f with the variable x is equal to this equation. G with the variable x is equal to this equation. Okay, so what we need to do here is we need to plug in values. So first of all, the very first question says, show that f at 2 is greater than g at 2. Or in other words, they write it like this. Oops, that's not enough. They want us to prove that f at 2 is greater than g at 2. What that means is they want us to plug in 2 for each of these and find out what they're equal to. So in our first one, we write f at 2 is equal to, and we replace the x with the number 2. And in the other one, g at 2, which is a different equation, 1 minus 2 times 2. So in the first one, we end up with 4 subtract 6. And here we get 1 subtract 4, negative 2, negative 3. So right there we've proven that negative 2 is greater than negative 3. We've just proven this part here by solving that part of the equation. Okay? So sometimes they'll rearrange the type of notation it's called. So you have to get used to seeing things like this, where they write g and a variable in it. All they're saying is plug the number 2 into the equation that g represents. Okay? Now, there's other things you can plug into these equations too. It doesn't have to be just numbers. For instance, in the second example, like we'll call it 2b, they tell you to determine what this is, G3b. Okay? What that means is they want you to take g at x, which is 1 minus 2x, and it's the same idea. They want you to substitute 3b in for x. Okay. So in this question, I'll write it just below, g at 3b is equal to 1 subtract 2, and I replace the x with 3b. Okay. Now I get 1, negative 2 times 3b. You know what that is?
-6b.
That's right. From there, are these like terms? No. Can I do anything to simplify that? That's it. So g at 3b is equal to 1 subtract 6b. So it's just another equation with a different variable involved in it. Okay. And then finally, the third type they can go and work with here. Here's another one we can solve. Example 3. Okay. The last example here, what they've done is instead of x, again, they have different inputs. They're putting in the letter c. Okay. Now, if you remember, we'll quickly write in red what the old equations were. F at x was equal to x squared minus 3x, and g at x was equal to 1 subtract 2x. Okay. So it says to determine this. So in other words, my first function here, okay, I'll kind of circle it in green here. My first function, they want me to take it, and instead of using the letter x, we're going to replace it with c plus 2. So in other words, we get c plus 2 squared minus 3 times c plus 2. And that is, and I'll end brackets around it again, that is the first function here. Okay, that's what we've just plugged in. It then says to subtract the next function, which I guess we'll outline in blue here. And the next function deals with this, which is the number 1 subtract 2, and it says to replace x with c plus 2 again, c plus 2, end brackets. Okay, so we're essentially subtracting two functions, but according to BEDMAS, we have to solve each function first before we can subtract them. Okay, so I deal with the green one, the one I've circled in green or bracketed in green, and I'm going to deal with the g, and then at the end I'm going to subtract all my like terms that I have. Okay? So in the very first one, c plus 2 squared, that's like a FOIL question. We get c plus 2 times c plus 2, and I'm going to distribute the negative 3. What's negative 3 times c?
-3c.
Yeah, and negative 3 times 2? That's right. Okay, so that's the first one. And in the second one, we have 1. And again, we distribute the negative 2. What will I get?
-2c plus -4.
Plus?
Sorry, -4.
Yeah, that's right. Minus 4. Now, on the next one, we technically have to FOIL. So let's do the first terms.
C squared plus c2, 2c.
Yeah.
Plus 2c.
Yeah.
Plus 4.
Good. Minus 3c minus 6. And the other one here, subtract. Can I collect any like terms?
1 minus 4.
Which is what?
-3.
So how will I write this bracket now?
-2c minus 3.
Good. Okay. So I've done that. These brackets here, the one we started with, technically like a positive one in front. So it won't change anything if I drop the brackets. So we'll just go to one set of brackets now. We're just going one step at a time. If you wanted to go faster, you obviously could. C squared. What's 2c plus 2c?
4c.
Plus 4c plus 4 minus 3c minus 6. Okay. I'm going to keep these brackets around the other part just for now. We'll drop them all at the same time. Okay. Now let's collect our like terms in here. Anything with c squared? No, so we leave it. What about 4c?
1c.
Yes, you're right. It becomes 1c. So plus just c. And what about 4 and negative 6?
-2.
Good. Can I collect any more like terms in there, or is that as simplified as possible? Okay. And that says to subtract negative 2c minus c. So let's finally drop these brackets. I'm going to get c squared plus c minus 2. Now what happens to this one here? Because it's a negative sign in front.
It turns, or it like flips the other ones.
Yeah. So what's going to happen now that the brackets are gone? What is it going to read?
Plus 2c
Yep.
plus 3.
Good. Are there any more like terms?
It's c squared plus 3c
Good.
plus 1.
That's it. So we've gone through it all. When we subtracted f at c plus 2 minus g at c plus 2, this is what we determined. C squared plus 3c plus 1.
So what was the question? Like the original question, what did I read?
Right here. All I said was determine this.
Oh.
Yeah. So that's what function notation is. You have to get used to reading what they're trying to ask you. So if they give you an f, you know they're referring to this function, and they want you to plug in this value for x. And for the g, if they give you g, you know they're referring to this function, and they want you to plug in c plus 2 for the x. And then what it really says is to subtract those two functions once you figured out what they are. So we, in our green one, we figured out our f at c plus 2. Our blue one, we figured out g at c plus 2. Once we got the brackets, this is what we got. This is f at c plus 2. That's the answer to that. And this is the answer to g at c plus 2. We then subtracted the both of them. Okay? And once we subtracted and collected like terms, this is what we determined was our answer for this original question. So they've given you this function, and in the function they've told you that this graph here is g at x. Okay, so this little graph here is g at x. We don't actually know what the equation is, they haven't told us. But for it, y is essentially equal to g at x, which is what we kind of talked about on the other pages. When we said we were plotting points, we said what we were plugging in was the input and the outputs were pretty much y values if you're going to graph them. So what they've done is kind of the opposite here. They've given us a graph of some equation. Now, we don't technically know yet what it is. It can be figured out, but for argument's sake, let's say we can't figure it out. They're asking us to find g at 3. Now, g at 3, if g at x is equal to y, that is a bit tricky. They've replaced x with what number?
3.
3. So on the graph, where am I looking?
3.
Yeah, I look on the x-axis for the number 3, which is right here. And I need to figure out what y is at that point. So what is y at that point?
2.
2. So in other words, we've just discovered that g at 3 is equal to 2. And that is essentially a coordinate, right? Our coordinate here, well, we can write it, it's equal to 2, and essentially that coordinate is 3 and 2. Okay. So in the next one, they asked us for g at negative 1. Well, we got to look for negative 1. What is it?
It is 1.
Is it?
Isn't it? Oh no, it's 0.
Yeah, so g at negative 1 is equal to 0. So is equal to 0, and that coordinate is negative 1 and 0. Okay. Now here's a little trickier one. C says, discover x if g at x is 1.
Okay.
What does g at x stand for? What did we say over here g at x was?
Y.
Y. So in other words, instead of saying g at x, find x if y is 1. So where is y1 on this? We're going up and down the y-axis. Take a look. Here's y1. What is g at x equal? Oh, sorry, not g at x. What is x equal to when g at x is 1?
0.
0, that's right. So, in other words, we'll do this one in blue because we kind of reversed it. We'll put an arrow down. Technically, g at 0 is equal to 1. Or in other words, x was equal to 0 there, when g at x was equal to 1. So the only difference from the first two, we were looking along the x-axis, that's why I did them in red there, We looked at -1, -3. Here they asked us to look along the y-axis. So we looked along the y-axis, and it just so happened that's where g at x, or y, was 1, and that's when x is 0. Does that idea make sense?
Yeah.
Okay. Now finally, domain and range. Have you done set notation for domain and range? In other words, have you seen something that looks roughly like this? Range being y-e-r such that. Ever seen that?
I don't think so.
No? Okay. So we got a bit to cover here. Domain and range, they're talking about when the function or the expression or the equation exists. Okay. So what I've written here is x, and it's an ER. And what that is, x is the element of all real numbers. Okay. So in other words, if this is a continuous, which this is, instead of having to write every value, because technically x is, see how it's here, it's -1. And then here it's 0. Oops, I shouldn't have done that. Stupid. There it's 0. There's actually tons and tons of infinite amount of numbers I could also say x is there. X also is -0.99 and -0.98 and 0.97. I'm not going to write all those out. That's ridiculous, especially since this is continuous. I have to write an infinite amount of numbers. So instead of writing all those numbers for the domain, I use this expression to cover all of that. What that means is XER, or x is the element of all real numbers. So what it's saying is x is every single number as long as, and I put this line here because there's a restriction. Does x exist to the left of -1? No, this function didn't exist, right? It just seems to start up there. So, in other words, x is every real number as long as x is greater than or equal to, where did it start? Start at, well, not quite -2.
I mean, sorry, -1.
Yeah, there we go. So as long as x is greater than or equal to -1. That's a funny bracket I just drew. Okay. So what that means is x is continuous, it goes forever, and this arrow at the end represents it will go forever, as long as x is greater than -1. Okay. Range deals with y. Okay. Same idea. Y is every single number. What's the restriction on y though?
Zero?
Is it greater or less than?
Less than?
So y is only less than 0. So in other words, it only
no,
exists down here.
Greater.
Yeah, it only exists greater than 0. Good. So we'd write this the other way. Okay. So y is every single number there, such that y is greater than 0. So that is your domain, and that is your range, which you're going to have to get a little used to. Okay. Okay. In the fourth example, this is like a reverse. Okay. The question asks you, when g at x equals 5, what is x? Okay. In other words, remember we said, what is g at x also equal to, or could it stand for? Another variable we sometimes use in graphing. Yeah. It's just like saying y is equal to 5, right? So if this really represents y, what they want you to do here is replace g at x, because they've given you the answer, with the number 5 to solve for x. So in other words, I replaced that g at x with my number 5. So I now get 5 is equal to 3x plus 5. And now I isolate for x, because they wanted me to find out exactly what x is, right? So my goal is to now isolate for x. When I bring 5 to the other side, subtract by 5, 0 equals 3x. What's x going to be?
Pardon?
What will x be here?
Zero.
Right? We divide by 3, still going to give me 0. So in this case, x is 0. Right? And they can ask us several. They could also ask you when g at x is 27. What is x, right? So same idea, we would take that function, we would replace g at x with 27 is equal to 3x plus 5. Okay, so now when I move 5 over, I get 27 minus 5, which is 22, equals 3x. X is going to be equal to, I divide by 3, right? 22 divided by 3. You can put a decimal or fraction form, but that would be your answer essentially. So you're finding out the x values when you already have your y values. It's just the reverse of it. Okay? So instead of plugging in a value for x, you plug in an entire value for the g and x of the